Alrighty. So, if you remember from Friday, we talked about parallelograms, right? And the key kind of concept that we had Friday is we learned a bunch of properties that were true as long as you had a parallelogram, right? So if you had a parallelogram, then, and what kind of things could we say about the parallelogram? Yeah.
Opposite sides are parallel.
Okay, that's the definition of parallelogram, right? If we have a parallelogram, by definition, opposite sides are parallel. But what other properties arise from that? Opposite sides are also what? Congruent. That's property one. What's another property that happens in parallelograms? Opposite angles are congruent, right? And then there was one more, but oh yeah. What about the diagonals? Diagonals don't have to be congruent. Corey? They bisect each other, right? And a quick, just to speak to Emma's question there, or not thought about, okay, well, do the diagonals have to be congruent? I mean, if I draw a parallelogram, you can kind of convince yourself and see, well, there's one diagonal, there's the other diagonal. Does it look like they necessarily have to be congruent? I know. Granted, I just drew this by hand, but you can at least kind of see here, doesn't necessarily. I mean, it looks like that one's going to have to be shorter than that.
I asked that question.
Oh, you asked a question?
No, I didn't know if I didn't
Oh, you didn't say that? Someone else said that? Okay, well, I don't know. I thought it was you. Anywho. Okay. What we're going to do today, is go in the exact opposite direction. Okay? What is enough information to say that something is a parallelogram? So again, before we started, if it's a parallelogram, then we know these things are true. Opposite sides are congruent, opposite angles are congruent, and diagonals bisect each other. What we're going to do now is go, what information is necessary to then say, guaranteed, this thing is a parallelogram for a quadrilateral. So, first property we're going to say here is that if both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. Aha! So this is exactly the reverse of that one property we learned on Friday, right? If we can show that both sides are congruent, both pairs of opposite sides are congruent, then we can guarantee the shape is a quadrilateral. The quadrilateral, is a parallelogram. All right, so here's our shape, drawn in the form of a parallelogram, but not guaranteed to be so because we don't know for sure that this is parallel to this or that this is parallel to this, right? All we have is that opposite sides are congruent here and here. So, to do this proof, to show that this does guarantee a parallelogram here, we're going to start by drawing a diagonal DB, much like we did for our earlier proofs on Friday, right? By drawing a diagonal DB, why is that helpful? What have we now created? Two triangles, and specifically we know these two triangles are going to be what? Congruent, yeah, okay. So this creates two triangles that we can prove to be congruent. Now, the proof is going to be different. We no longer have parallel sides, so we can't necessarily use alternate interior angles here and stuff like that. But it's not really necessary, okay, to require to get some angles here, right? So we're just going to prove this in a slightly different way, but still trying to prove these two triangles congruent, okay? So we go down to the actual proof here. Okay, we start like we did here by starting with the diagonal DB, and then we can say that segment DB is congruent to itself by what property? Reflexive property. Okay, we can then say that AB is congruent to CD and AD is congruent to BC. How do we know that those congruences are true? Well, be careful. We don't know this shape is a parallelogram. How do we know in this particular instance that those things are true? It's given. It's given information. Yeah, we're given that information, so we don't even need the property in order to do it. As a result, then we can go ahead and say triangle ABD is congruent to triangle CDB. Why? Side side side. Okay, exactly right. So then we have that ABD is congruent to CDB. So ABD, CDB are congruent. And then ADB, this one right here, is congruent to CBD. Like that. And how can we say that those angles are congruent? How can we say that this pair and this pair are congruent? CPCTC, you got it right there, Thomas, exactly right. Okay? Corresponding parts of congruent triangles must be congruent, matching parts. All right, and then we can finally say then that AB and DC are parallel and AD and BC are parallel. Why? What kind of angles are these?
Alternate.
Yes, they're alternate interior. So now because we're using the alternate interior to prove that we have parallel lines, it's the converse of the alternate interior angle theorem. And you can abbreviate. I'm just going to put alt-int theorem. Okay, you could abbreviate theorem too. I don't know why I didn't do that. Okay, the converse. Okay, the reason why I have to say it's the converse is because the normal, like just alternate interior angle theorem, states that if you have parallel lines, then alternate interior angles are congruent. The converse says if you have alternate interior angles congruent, then the lines are parallel. Okay, so that's the idea. And then finally, ABCD is a parallelogram. And how do we know that? By the definition of a parallelogram, right? We've got opposite sides parallel. And so once you have opposite sides parallel, then that's in a quadrilateral, that's a parallelogram. Okay? So, the proving of a quadrilateral being a parallelogram, for example, in this case, right, is just an extension of what we already know with congruent triangles. Okay? So it's not like not much crazier, it's just we're just using congruent triangles to help us there. Okay? To prove this property at least. Questions on any of this? Okay. So now if you see opposite sides congruent, two pairs of opposite sides are congruent, then you're guaranteed to have a parallelogram. Okay? Turn the page there to page 434. At the top, you have another proof, not a theorem, that says if one pair of opposite sides of a quadrilateral are parallel and congruent, then the quadrilateral must be a parallelogram. Okay? So that proof, we're not going to do that one, but it is a true statement here. If you've got one pair of opposite sides that are both parallel and congruent to one another, then the quadrilateral is a parallelogram. Okay, guaranteed. All right, got a reflection question here. Number one, discussion. A quadrilateral has two sides that are 3 centimeters long and two sides that are 5 centimeters long. A student states that the quadrilateral must be a parallelogram. Do you agree? So we have a quadrilateral, a four-sided shape.
Yeah.
Two sides are 3 centimeters, two sides are 5 centimeters. Is that enough to say it must be a parallelogram?
No.
No, why not, James?
Any sides.
So yeah, what? Go ahead.
Like the two vertical sides can be, one could be 3 and one could be 5.
Okay, right. So what must be true about these 3 centimeter sides? If it's a parallelogram, those 3 centimeter sides must be what? Opposite of each other. Are we told that here? Not necessarily. So we could end up with a shape that kind of looks something like this. 3, 3, 5, 5, like that. Okay. You guys know what the name of that shape is? It is a kite. Yeah, that's
Wait,
right.
is that actually-
No, it is really a kite. Yeah.
Oh, yes.
Okay, there it is. Whee! There's Alex holding her kite. Okay. No, but it is called a kite, and we're actually going to study kites. It's actually a geometric term, believe it or not. It is a kite. Yeah. Okay. So there it is. Sometimes we name things appropriately. Sometimes it's weird names we make up. All right. So sorry, page 434. Page 434. Okay. All right. Let's go then. Continue on here. Good answers there. All right. Proving the opposite angles criterion. So if we have opposite sides congruent in a quadrilateral, it's a parallelogram. And if both pairs of opposite angles of a quadrilateral are congruent, then the quadrilateral is also a parallelogram. All right, and we'll do this proof here too. There's just some blanks for us to fill in. They're doing it in a paragraph proof style, but it's actually easier than the other one, I think. So given that angle A is congruent to angle C, and angle B is congruent to angle D, we're going to prove that this shape here is a parallelogram. And of course, again, it looks like a parallelogram, but we don't know that opposite sides are parallel yet. We have to prove that, right? It looks in the right form, but we need to show that it's actually parallel. These are parallel and these are parallel. So we're not going to use congruent triangles here. We're going to use something else. We're going to use the interior angle sum, right? Isn't this true that A plus B plus C plus D has to make 360 by the interior angle sum theorem? Okay, the interior angle sum theorem.
Is that not specific to a certain shape?
Correct. It's not specific to a certain shape. You can use that for, you could argue that for a triangle too. Yeah, any polygon you could say. Okay. And I would also, of course, read, it would be you'd have to consider who your audience is, whether they would know what they mean by interior angle sum. You might have to say the interior angle sum says that n minus 2 times 180, kind of thing. So, but yeah, this is fine for our purposes. You guys know what this is. So, from the given information, the measure of angle A is equal to the measure of angle what? C, right? We're told. And the measure of angle B is equal to the measure of angle D. By substitution, therefore, where we had A plus B plus C plus D, we can substitute in for B. No, letter D here, right? Yeah? So I'll put parentheses around that. We substitute that in. And then angle C, we substitute in angle A. And so now, instead of A plus B plus C plus D, we have A plus D plus A plus D equals 360. Or 2 angle A's plus 2 angle D's is 360 degrees. We can then divide both sides by 2, and that would give us the measure of angle A plus the measure of angle D equals 180 degrees, right? If we divide the left side by 2, those two 2's cancel out, and 360 divided by 2 is 180. Okay. So therefore, angle A and angle D are supplementary, and so, since angle A and angle D are supplementary, AB must be parallel to DC by the, what special angle relationship are these? Same side interior angles. Yeah, so the converse of the same side interior angles theorem. Or co-interior, if you remember that way. Okay. Now, all we've proved there is that AB is parallel to DC. We're not going to bother showing AD is parallel to BC. It's like a similar kind of argument. You just kind of like, change a little bit about how you do the proof. Okay, so we're not going to do the whole thing. We'll just say, that ABCD is a parallelogram by the definition of parallelogram here. Okay. By a similar argument, you could say, instead of saying A plus D plus A plus D, you can make it B plus C plus B plus C. And then do 2B plus 2C equals 360. So it would be B plus C equals 180, and then they'd be co-interior, same side as side. I guess we need to do A and B, or D and C. Never mind. My apologies. We need to say A plus B, or D plus C kind of thing. So anyway. Okay? All right. Yeah, we'll skip number 2. I think that's a little too silly, too easy. All right. So again, how can we tell if something's a parallelogram? If opposite sides in a quadrilateral are congruent, or if opposite angles in a quadrilateral are congruent, then it's a parallelogram. Okay? And then our last property we're going to concern ourselves with is, again, the third property we talked about on Friday. If the diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. So essentially, these properties go both ways, right? If you have a parallelogram, then you can say opposite angles, opposite sides, and diagonals bisect each other. Okay, opposite angles and sides are congruent, diagonals bisect each other. If you have a quadrilateral that has opposite sides congruent, opposite angles congruent, or the diagonals bisect each other, then you can say for sure that quadrilateral is a parallelogram. Okay, so here we've got a quadrilateral where the diagonals are bisecting each other. Okay, so we'll go ahead and run through this proof here. AE is congruent to CE, DE is congruent to BE. So that is given information right there. Okay. AEB, this angle right here is congruent to CED, this angle right here, and then AED, this angle and this angle are congruent. How can we say that those two pairs of angles are congruent? What kind of relationship is that? They are vertical angles. Okay? So with that information, step 3, we have triangle congruences already. We could say triangle AEB. AEB is congruent to triangle CED. And we can say that triangle AED is congruent to triangle CEB. By side angle side. And then how can we say that these parts must also be congruent? CPCTC.
Oh, was that right?
That was right.
Oh, sweet.
Okay, yes, CPCTC. They're corresponding parts of congruent triangles. They must be congruent. And here we can say ABCD is a parallelogram using one of our previous theorems. Okay, since we have now that opposite sides are congruent, okay, both pairs of opposite sides are congruent. Maybe I should say that too. Both pairs of opposite sides. Both pairs of opposite sides are congruent. So that makes a parallelogram by one of those previous theorems that we talked about. Okay. We're going to skip the explain 3. We don't have to worry about that. Moving on. Okay, we'll do 2 more problems here together, and then we'll have you guys try some, and then we'll get started on the homework. Okay, so now we've got a shape here, and we want to show that this quadrilateral is a parallelogram for the given values of the variables. All right. So we've got 5y minus 4 is this side, but we're told that y is 4. So we can just plug the 4 in for the y. Same thing here, there's a y, so we'll plug 4 in for y. So 5 times 4 is 20, minus 4 is 16. 2 times 4 is 8, plus 8 is another 16. So that side 16, and that side 16, right? X is 7, so 7 plus 14, 21. So that side's 21. And then 3 times 7 is also 21, which again, that side's 21. So, is this shape a parallelogram?
Yes.
Must be. Why?
Because they're the same.
What are the same?
The sides.
The opposite sides are congruent, right? And I know that you meant that, Charlie, but again, it's important that not just for me, but like, you know, should you be trying to justify yourself to someone else, you want to mean what you say and say what you mean, right? Okay. Be descriptive. All right? But that's right. Very good. All right, one more here. Here we got some angles. Okay, what are we told is z? 11. So that means this angle, 9 times 11 plus 19. So, whoops, I don't need that parenthesis there. 9 times 11 is 99. Plus 19 is 118 degrees. Okay, do the same thing here. 11 times 11 minus 3. 11 is 121, minus 3, 118. Okay. What's W? 4.5. Okay, so 14 times 4.5 minus 1.
63.
Is it 63?
62.
62 when you take away the 1?
Yeah.
Okay, 62 degrees. Oh, that makes sense because it's got to be supplementary. Well, hopefully it's supplementary, so that's a good indicator right there. And we'll do this one here, 12 times 4.5 as well, plus 8. So, yep. Oh, okay. So 62 degrees for there. And so then is this shape a parallelogram? Yes. Because
Opposite sides.
opposite angles are congruent. Yep. Very good. Yeah.
Do you need to do both of those to prove that it's a parallelogram?
Like, I think, like, once we had this 62, was it necessary to have this 62?
No, I mean like just one pair of angles.
I think, yes, because a kite is a quadrilateral that has exactly one pair of sides, or one pair of angles are congruent. Like if I drew in the kite, typically these angles are congruent, but very clearly these angles are not going to be congruent there. So there's a quadrilateral that has one pair of congruent opposite angles. Now, once we had this 62, so we had the two 118s, and then we had this 62, I think by that point then, we're good to go. Because co-interior, bless you, co-interior, that was a little squeaky. Okay. So, all right. So turn the page, and you guys try 6 and 7. Y'all try 6 and 7. Okay. Now, what you should not do here for number 6, I do not want to see people write this. Don't want to see that. Okay, why can't we write that? We don't know they're equal yet, right? We don't know they're equal. So you got to plug in and see if they're equal. That's what we're trying to do. We're not setting these equal and solving for A. Yeah, you could like kind of do it that way, but it's like kind of assuming something that's not true, and we don't want to start off by assuming something that's not true necessarily. We don't know it's true, so we want to be careful with that. Okay, so please.
Wouldn't that just be like a way to find what A is?
And then if it matches to the 2.4, you could then say, you know, they're the same. So I mean, it's kind of a way to do it, but it's not great math because you're assuming they're equal to then show that they're equal. So yeah. It would work, yeah, it would work. It would work.
Because then if it doesn't like add up, then it just wouldn't be equal.
You wouldn't get necessarily A is 2.4 there, but again, it's the more mathematically appropriate to like check the values for those particular things and see. So. All right, so again, give those a try. 6 and 7. Question? So our opposite sides are on top. How are these related?
Oh, they add up.
So this is that. We didn't prove this one, but it's this right here. If one pair of opposite sides are quadrilateral, are parallel and congruent. So they're congruent, but they're also parallel because same side interiors are supplementary. So that makes them parallel and congruent. One more minute here. One more minute. One more minute. Oh, your distraction? Okay. Okay, there it is. All right, 14, 14, 22, 22. Yes, it's parallelogram because diagonals bisect. Here, This one's a bit unique, right? This is that one we didn't prove this one. We kind of skipped this one. All the other ones we did prove, and we didn't talk about this property when we talked about parallelograms on Friday. But it is true, okay? If opposite sides, if one pair of opposite sides are congruent and parallel, and they're parallel because we have supplementary co-interior angles, congruent obviously 16.8 to both of them, then it's a parallelogram. Okay, that's one additional kind of thing. So if one pair of opposite sides are both congruent and parallel, guaranteed that shape is a parallelogram as well. Okay? Last thing I want to talk about before I cut you loose on your homework is number 10. Okay? So, what are 3 different ways that we could show this quadrilateral here is a parallelogram? So, way 1, Idris. Opposite sides are equal. Great. Okay, what's another way? James? Opposite angles are equal. Okay, and Reed? Probably? Yeah, I think we could prove that. Yes, no, we could prove that. We could prove that. Let's think about drawing in a diagonal here. And think about drawing in a diagonal here. I think we could prove that by using like congruent triangles. Because this is going to be a 45, 45, 90. That's going to be a 45, 45, 90. So I think it could work. Yeah. So I think that'll work too. Yeah. Yep. Okay. So yep. Very good, folks. Very good. Okay, so let's get you guys started on your assignment. Okay, it is on the Google Classroom, but I'll put it on the board here too. Just so, whoops, wrong program there. Okay, here we go. Page 439. Numbers 1, 5 through 12, 14, 15, 18, and then if you want to try, there's a challenge. Oh, there's a challenge one I was going to point out. Did I circle that? Where did I put it? Number 20, if you want to try number 20 for some challenge. If you're asking for a challenge. If you wish to accept the challenge. Just a little bit of algebra refresher. Yep. Go for it. Sure, go ahead. Okay. And of course, there's the TenMarks too.